Hello everybody. We are going to be talking a little bit about motor systems and controls. Hence the word that says systems and controls up here for the astute observer. Now, the last lecture that I recorded, I went over an example that was about a forklift system and lifting something that's up off the ground. And as a result of that, we produced an open loop feedback system. I'm going to be talking a little bit more about a different type of system, this time a closed loop feedback system, just to get you all caught up again, hopefully feeling comfortable about modeling systems, the interactions, understanding the complexity of the systems that we're dealing with. So we'll go ahead and just start with our example. So here what we're going to be doing is, I don't know if you've ever seen it, but there are, like if you've ever had a drone, a really high-end drone, there's a gimbal system that is basically a platform that is connected to a series of motors and linkages, things like that. It's actually a three-dimensional thing. I'm trying to figure out how to draw it nicely. It would also help if I had one right here, but it's whatever. Right here you'll have a motor that's connected to this axis. You'll have a motor that's connected to this axis so that it rotates in this plane, and then you'll have a motor that's connected to so we have this axis, we have this axis, and then we've got this axis. So here you'll have another bar here that's connected to a motor, and so here this one will control rotations about this axis, this one will control rotations about this axis, and this one will control rotations about an axis that comes out of the board. Okay, so those three motors, this is pretty common for a gimbal system. It's pretty simple, but there are issues that come up with this. Now the idea here is that you will have a rate gyro sensor that is placed somewhere on the plate. What a rate gyro sensor does is it rate gyro. It measures angular accelerations. And if you get a 6-axis rate gyro accelerometer, 6-axis. What that basically means is that it measures accelerations in the X, Y, Z, rotation in the X, rotation in about Y, and rotation about Z. Okay, so a rate gyro, if you put it on here, it has the ability to measure all of these. Now, what this is specifically going to be focusing on, because the idea is it wants to be level relative to the Earth, it'll just specifically focus on these three. Fun fact, rate gyros only work in the presence of a gravitational field, because the gravitational field is itself what is causing the changes that the rate gyro is measuring. So if we didn't have a perpendicular, straight down gravitational field, the rate gyros wouldn't work at all. So this is the basic system that we have. 3 motors, each controlling rotation X, rotation Y, rotation Z, and then we have a rate gyro that is ultimately measuring it. Okay. So what does the system look like for this? Well, I guess before we get in there, I briefly mentioned this in the previous video, and I thought, you know, it's probably a good idea for me to expand on this a little bit more. When it comes to outputs, okay, outputs of components usually in a system diagram, we really only talk about one single output, but in reality, there's hundreds, thousands of outputs. I think I did a pretty good job of explaining to both of your classes that outputs from a system can be infinite. You can talk about radiation outputs, you can talk about heat outputs, you can talk about all of these different features. And really what it comes down to, what really boils down to here is there are always power and energy. Where is the energy coming from the system? Where is it going into? What kind of energy transformations are being made? Anytime you have current flowing, you're going to have a small magnetic field that's generated, or possibly a large magnetic field that's generated. There is some energy associated with that, and that is some of where the power is going. So you can talk about how magnetic field generation is one of the outputs of the system. Now, how does that magnetic field interact with other components? If other components around it aren't magnetic or influenced by magnetic fields, then there's no, that's the output. You just have magnetic field that's being produced by a component. Every time you plug in and charge your smartphone, there's a small magnetic field that's created around there, and it could be influencing things around it, or it could not be. Depends. But that's one of the outputs. It is a source of power loss, is that there is a generated magnetic field in the presence of an electric current. Okay. The topics that we talked about yesterday too were, we also talked about efficiency, but we also talked about error. Efficiency kind of has to do with where the power is going, how the power is transmitting. I'll include that up here. Because if you want all of your power to go into mechanical, but some of that power is going into heat, you're going to have a lower efficiency. You do have an error calculation that's coming out here. You do have time functions, because every single component has some element of capacity, some element of an inertial component, a capacitive component and an inertial component, and a resistive component. We talked about real systems. Real systems have all three of those present: capacitive, inertial, and a resistive components, or a dissipative component. And that's going to affect how the time function works for that item. How does the input to the output, how much time does it take for that to occur? So not only do we have error being information. If I put in 3 pounds of load, but I only get 2.8 pounds out because there's a little bit of friction in that joint, and there's 2.2 pounds that's going elsewhere because of that, we do have that error that's being transmitted. Okay, and so here we've got power, we've got error, we've got time functions. Time functions is just, as we mentioned yesterday, it's latency. But there's also a series of other things, vibrations. And this doesn't have to be a physical mechanical vibrations. This could actually be an electronic vibration, which is what is the frequency spectrum that's being put out. We talked a little bit about doing an FFT and determining the frequencies that were present. Everything has a frequency associated with it. Even talking is a frequency. There are frequencies present in everything because everything is vibrating. It doesn't matter if it's an electric signal, doesn't matter if it's a digital signal, doesn't matter if it's a power source, doesn't matter, everything is vibrating. And we have to deal with the series of vibrations that are going on. Part of power, too, is discussing heat. I'm mentioning it specifically, even though, yes, it is a piece of the power analysis, but every system generates heat. Every single one. The degradation of energy, it turns into heat because it is the highest, I don't know. Yeah, I don't remember what I was going for. It's a thermodynamic term, and I did not bring my thermodynamic brain this morning. Great. But it's the lowest form of energy is heat. And so everything goes to heat. There's always going to be a heat analysis here. Addition to power, if you just kind of keep on the trend of power, there's always going to be, for every power, there's always some displacement component, and there's always some force component. And anytime you have a power transfer, you may specifically only be focusing on displacement or force. You may also be focusing directly on power. Regardless, these are outputs of the system as well, and you can even further break, a displacement down into, you've also got your velocity and your acceleration, both of which are functions of your displacement. It's just a derivative function. But then additionally, your forces also have other pieces that go along with them. You can have a momentum, because their systems are going to have some momentum associated with them. But you can also have, in addition to just momentum, you can talk about impulses and those types of things. So really, when it comes to the output of a system, we can really get into the weeds on different types of power, the displacement elements of those power, the force elements of those power, the velocity elements of those power, the acceleration components, the momentum components, the impulse components. There are just so many different outputs you can put into this. At the end of the day, again, for our purposes, you can always identify yet another output. You can talk about the displacement velocity at any point on the system, which may be different from the point next to it. That's already, however many hundreds of different outputs that you can generate just by changing the location of where you're looking at on the component. So keep this in mind. We're not going to be able to identify all of the outputs. We're just looking to to try to understand, when you go to build your model, the goal of building your model is you want to have an input that you understand, you want to have some kind of a processor, and then you want to have some kind of an output. Very, very simple model of this. And you may have several inputs that all participate. You may have several outputs that all matter to you, but usually you really only focus on one. You build systems for each output that you want. And it can mostly be the same system, but usually I like to focus on one single output. It's a lot easier to put inputs than to just do outputs. But this is what we're trying to do. Okay, so we focus on what is it the output that we really want, and then what is the process by which we ensure that that output occurs. Okay, so specifically looking at what is the orientation of this plate, we want the output to be orientation of the plate. Okay, what is the input? Well, here, the input could be a number of things. This thing could actually be moving. This thing could be shaking. There could be a time variant forcing function that is being put on, if we call this the host body or whatever and this is the symbiote that's just coexisting peacefully now. But if we call this the main body of whatever component it is that we're looking at, let's say this is a drone. If we have this main component, the gimbal is hanging off of it, but this main component is going to be experiencing forces. We've got our 6-axis forces that this is going to be facing. And we're going to be experiencing accelerations in the XYZ directions, angular accelerations about the XYZ axes. So that's your 6 axes again. And how does this account for all of those different types of movements? So the input to this is really going to be what I'm going to go ahead and call error. Okay, now I know I've already used that term, but the idea here is that, we'll talk about this in a second, but we're actually we're going to assume that this system is generally stable, just stays still. We want it to stay still. And then the input then is what happens when the system is not still. And we're going to go ahead and call that error. Now, before we move forward, let's define error. In systems and controls, different classes have different definitions of error. In a measurement, I guess we'll go, when it comes to a measurement error, this is something like, what is the actual state versus what is the measured state? Okay, so for example, if I go to measure one of the walls on my house, I use a tape measure, I get out there, my tape measure isn't exactly straight, it's a little crooked all the way across, and maybe my end point of my tape measure doesn't exactly touch the wall when I go to read the measurement. There are a lot of ways that I can introduce an error into that measurement. And so if I read that my wall is 23 3/8 inch long, but in reality my wall is actually 23 and 7 3/4. 3/7. Why do I want to say 7 so much? If this is the actual length of my wall, but this is the length that I'm reading, the error here can be seen in a couple of ways. And this is a measurement error. It could either be seen as it's a 3/8 inch error, or if I pull out my calculator quickly, I could also simultaneously say that instead of a hard value for an error, it's also a percentage error. So if I take 3/8 of an inch, which is 0.375, and then I divide that by what the actual measurement is, 23.75, my error value is associated with, so this is actual minus measured divided by actual times 100%. Okay, so then this would equal 1.57% error, okay, which really isn't very good. A 1.57% error is pretty bad. Unfortunately, it's not uncommon in the construction world. Measurements are not exactly easy to do. But here, this is a measurement error, and this is an example of a measurement error. But there's actually more than one kind of error. There's error associated with statistical populations where the error is the deviation from the norm. And there are errors, and there's just errors in a bunch of other classes. When it comes to this class, it's important to recognize that we're not talking about error being a measurement error. We're actually talking about error being a control systems error. Also known as just a system error. Okay, so when it comes to a control systems error, what happens is, this is the difference between the desired behavior, also known as the ideal behavior, and the actual behavior. Okay, whereas measurement error is oftentimes reported as a percentage, your system error usually is not reported as a percentage. It's actually coming in as a power. It's coming in as a displacement. It's coming in as a force. All of these things are relevant to being able to understand what kind of system error you're dealing with. So it is very similar in definition, but the key difference here is that it's not the actual versus the measured. It's what you want versus what actually exists. And here the what you want is kind of the important piece. So yeah, if we were to come up with a percent error here, the irony is that the calculation is almost exactly opposite. It's the desired minus actual divided by desired. Whereas before it was actual minus the measured. Here, we don't even care about what the measured version is. We only care about what we wish it was happening. So when we talk about error here, in a control system, this is oftentimes what we're talking about. We want the system to have a certain input, and we want that input to look like this. But in reality, the input doesn't look like this. So if you have a drone, there's going to be eddy currents. There's going to be weird wind flows. You know, every once in a while, you're going to get close to an object with your drone, and one set of propellers is actually going to be more powerful than the other set of propellers. And it does create an instability in the system. Just like me going in and out of focus in this video. Sorry, you can't hear all this rave music that's going on in here, but it's rave day. It's Friday. I just watched that. It was disgusting. I'm a shameful human. So much shame. Anyways. So we've got this system here. How does the control system work? Well, here, instead of having a direct input, we just want this thing to be constant. That's it. Stay flat. And that is actually something where there is a programmed design state. So not only is there an input of error, but there's also an input of here's what I want the orientation to be. Okay, and this is a data value. How do you communicate orientation? Well, I say, hey, I want it to be flat. The word flat has implications of I want it to be this in the x-axis, this in the y-axis, this in the z-axis. Okay, that's what flat means. So here we do have two distinct inputs, and this orientation is a pre-programmed statement for the intent of what they want the system state to be. So here, this is what I want it to be. I want it to be pre-programmed. I want you to stay flat. Okay, so that's kind of the idea here. We do have two different inputs, and you'll notice this is actually the desired input. I want to tell you what I want the orientation to be, and then here this is the difference between that desired input and the actual input. Okay, so when we go to build this control system, we're going to start with just the pre-programmed, here's what the orientation is going to be, okay? More than likely this comes from a controller, so if you really want to continue building out this direction, there's a controller over here. The controller is pre-programmed, and the source code actually comes, the orientation comes from the controller. It's built into the memory, okay? But now what happens is this orientation value, is pre-programmed orientation value, it's stored on the controller, but it goes into the controller, and the controller says, all right, based on what I want this orientation to be, I'm going to go ahead and output a voltage value that will control the servo motors, the 3 servo motors here that are controlling this very simple gimbal. So it outputs and this is a piece of information. It is a piece of information that comes with power. There's a little bit of a power associated with it, but it outputs a piece of information, And then you have an input power from another source that takes that. So here it's, this would be a servo command. Depending on the type of servo motor, it could be like, hey, you know, I want you to be at this position. Here's a series of ones and zeros identifying the position that I want you to be at. Some servo commands are actually just analog signals, and well, relative to maximum, go this far. So you could have, well, it's a whatever thing, and what that does is it goes into a motor controller. And here you have your outside power that's coming in. Here's probably electric. That comes into the motor controller. And what the servo command does is it says, okay, here's how we're going to route this power. Here's how we're going to send it to the motor controller. Here's how we're going to send it to the actual servo motor. And what that does is it affects the or rotation, which is the orientation. Now, it would be easy to just say this is the output of the system. This motor rotates, the end. The problem is that that's not the end of the system. As you can see, there is actually some linkages, there are some connections here that go between each of these motors. The motor axis here doesn't align directly with this gyro. So what we end up having is we have a series of linkages, and these series of linkages are connected to the servo motors in order to turn that rotation into an actual physical movement. Okay, so it goes into a linkage system that outputs orientation by connecting them all together at some plate. Now this is nice. This is all great, but this is an open loop feedback system. We didn't even put in the right gyro here. Here I've labeled the components above each of the boxes. We can come up with our transfer functions for each. So here, the orientation, the transfer function usually just ends up being a, is it good, is it bad? We'll talk a little bit about how we introduce error here, because you'll notice that there's not an error put into this per se. But what you end up with here is, I'm going to go ahead and throw error into this linkage, just because there is some amount of error associated with the linkage changing movements, but also this piece that all of these motors are connected to are also experiencing some kind of an error. So this linkage ends up inputting an error, which is what happens when this thing changes. How does the linkage orientation change? And how does that then sum with the rotation of each of these joints to procure a position for that motor? But you have the error coming into the linkage, and what we end up doing here is we have this rate gyro that's placed on top of that plate, well, on the bottom of that plate. And what is that actually measuring? Well, it's actually measuring, if we go look at all of our outputs here, it's not measuring the intended orientation, it's not measuring the servo command, it's not measuring the power that's being sent to the motor controller, it's not measuring the rotation of the actual spindle, it's actually measuring the orientation of the plate. And that's what it is, and this is why we have to go all the way to orientation rather than just stopping at rotation, because it's not measuring just the rotation, it's actually measuring the orientation. And this output, the orientation, and then goes into the rate gyro. And what is just a position, a movement, a small amount of acceleration, what this has done is it actually turns into a digital signal indicating information. Okay, so input is actually a physical rotation system, output is an electric signal. Okay, so here this is digital signal. I'm just going to write digital signal. Okay, now this digital signal, what happens is that this digital signal is sent into the controller. That indicates here's the actual position. Okay, and this identifies our feedback loop here. So now we do have the presence of error. The error is influencing the actual, the error is being put into the linkage as far as what the rotation of that linkage is. And then as that error comes in, it changes the orientation. The change in the orientation is measured by the rate gyro. It comes back to here and it says, well, okay, here's what I want the intended orientation to be. Here's what the actual orientation is. And even though we are introducing error, what we end up having is that I'm even going to go back one step further. This is the intended orientation. I'm going to put this into a summing node where it's plus, minus. And so what happens here is we're taking the rate gyro and we're directly comparing that where we subtract what the actual value of the orientation is as compared to the intended orientation. And then instead of just sending both of those into the controller and summing them in there, we're summing them in the controller. Yes, the summing node happens inside of the controller. This is all technically one piece. But this does show you that the error is what's being sent into the controller is not, here's what the intended orientation is. It's actually a signal of, here's how we need to shift. And this is your system error, okay? So we're sending an error value into the controller. The controller then says, okay, well, this is not 0. If it was 0, it means it's measuring that the actual orientation and the intended orientation are the same. So you have no error, which is great. If you have no error, you have no servo command. If you have no servo command, you have no power. You have no power, you have no rotation. You have no rotation, your orientation stays the same. Okay? If your orientation stays the same, and it's being read by the rate gyro as the intended orientation, it goes into the summing node, these are still the same. This sums to 0, and we continue to have no movement in the system so long as this summing node is indicating that there is 0 amount of error present. Okay? So just keep in mind here, there are 2 different types of error that are listed on this exact same thing, and that neither of those take into account the fact that there may be error that is present here. As we talked about in the last one, error is what happens when you have the actual versus the measured, or the actual versus the intended. You have, if you would send a servo motor here, there's a certain amount of error associated with the motor controller receiving the servo command. For example, let's say this servo command is a 12-bit signal. Okay, a 12-bit signal. It's a 12-bit signal. Let's say it's at 5 volts. It means that it only takes, even though it's 12 bits, there are 4,096 individual steps involved in this 5-volt signal. So if we actually look at how this servo command is being put up, what it's doing is it's saying, okay, this is what you want to come out of here, the value of the command. Nope, this is the value of the command. Desired output. Dis. Wow, I'm dyslexic today. So here, if I want to indicate that there is this value here, then I would go up and it would say, okay, well, the value of that command is going to be this. But if I go slightly to the left, the value of the command is still going to be the same, because there's only 4,096 individual steps that can possibly be sent out by the servo command file. Even though it's a 12-bit signal, you only have 4,096 different commands that it can give, and they're increment up. We could change this to a 16-bit signal. 16-bit signal would be something like 64,000 steps. It does make the steps a lot smaller, but there's only 64,000. If we want to have a slight change between this value and this value, the problem is that the command that's sent to the servo motor is going to be the same. Okay, so it's a resolution error, but that error still exists in that now you can't have anything less than the 4096 bit resolution, the 4096 stepped resolution. You can't have anything better than that. So there's an element of error that's associated there. Here there's an element of error that's associated once this has gone into the motor controller. There is a possibility that your motor controller is going to have a linear scale for what the output of that power actually is. So this may say, okay, I want this amount of power to be output, but in reality, if you go down here, there's only this amount of power that's being output. Okay, that's another source of error. You go into the servo motor, some of that power is going to be consumed by the electric wires. So not all of that power is going to go into rotation. One of the nice pieces about servo motor is that it actually ends up taking the servo command directly, even though the power here going into the motor controller is shown this way. The servo command ends up being routed to the servo motor so that it doesn't end up being influenced by all of the other components. And this does allow the controller to directly tell the servo motor, here's the position that I want you to be in, rather than relying on the power value to say, okay, well, get up to here. Okay, now there's going to be some error associated with that rotation. Okay, there's some flexibility in that line. There's always going to be, it's going to be in the tens of thousands of places, but there's an error associated with the intended rotation and the actual rotation based on the load that's being put on that shaft. And similarly, there's going to be some flexibility in the linkage. Your joints are going to have some flexibility, and your components are going to be flexible. As they handle load, as they handle vibrations, they are going to shake slightly. It's not very much. Again, you're still talking probably in the tens of thousands, but there is still some error associated here. So here we then have error that's being propagated through. That error is a result of the fact that these are real components and not ideal components. You have that type of error. You have this type of error, which is usually a force, a rotation, 6-axis input that's being put into this linkage to indicate how this is shifting, how it's moving. So you have this type of error. You have this type of error that's being put into the controller, which is an actual data value called error, which is just the difference between the actual and the intended values. And then you have the error that's associated with a measurement error, the intended value versus the propagated value. So 3 different kinds of error on this exact same drawing, and all of them are very distinct. It can be a little bit confusing. So this is an example of a feedback loop. Again, I didn't write in each of the transfer functions. You could take those transfer functions and you could ultimately solve this system. You end up with a system of equations where you have input in some function of the input equals some function of the output, and then this output variable is plugged into the next one, which is some input, which happens to be this value here, doop, doop, is equal to some other function output. Okay, and you end up getting these functional relationships at each one of these boxes. And each of these systems of equations can be can be plugged into a matrix and solved using a matrix to ultimately find what the orientation as a result of all of this is. We did talk a little bit about matrices in systems and controls. So the overall goal here is if you can come up with what these functions are, you can plug them into a matrix and then solve that matrix, which is pretty simple. The work make the computer solve the matrix. The other nice piece about having a system of equations is you can take those systems of equations and actually put them into an ODE solver and have the ODE solver solve it for you. So you don't really have to do the math. You just have to be able to interpret the results. And here then it says, okay, if I put in a value of 15, I'm going to get out a value of 18, something like that. And you have to know what those values mean, what the ultimate measurement is, that what is the unit on the 18? What is the unit on the 15? According to how you set up your equations, those units should be taken care of. So, all right, that's going to be it for this video. I will see you all on Monday.